Hello, everybody. So in this lecture, we're going to continue the discussion about distribution, but for several variables. So last time I have already reviewed or sort of introduced basic definitions about distributions. So especially test functions, the notion of convergence in the space of test functions. So these are exactly the same thing, except that we are going to use partial derivative with multi-index instead of just the simple derivative. And the distribution is defined to be a continuous linear form on the space of test functions, right? So a continuity in the sense that in the sense of the second definition, when we have a notion of convergence on the space of test functions, and this is equivalent to this kind of inequality that we show all the time to prove that a certain linear form is a distribution. Then partial derivative, product of a smooth function, restriction of T to a open set. These are all exactly the same as before. The support of a distribution also the same. Convergence exactly the same, and the order, they're all the same. So in such a situation, so I mean, in higher dimension, the statement of most results previously obtained in one dimension, they are still the same, right? So we don't need to change a thing. Also, we don't need to change the statement, neither the proof. So this is good. On the other hand, some of the results are more complex, and also the statement needs to be slightly adapted. So this is the goal of this lecture. We're going to show some of those new statements which are more complicated than their one-dimensional counterpart. And the first thing I want to show is about the restriction and support. So we're going to look at the proposition 7.2. It's called a Guluing principle. So here we consider a collection of open sets, and we denote the union of the collection of open set omega, which is still open set. We suppose that on each of the omega j, we can find a distribution such that this distribution Tj and distribution Tk coincide on the intersection of the two sets omega j, omega k. So somehow we have a consistent family of distributions defined on the family of open sets omega j. So if this is the case, then we can find a unique T, a distribution on omega, which is the largest set of everything. So this is the union of everything, such that the T restricted to omega j becomes Tj. So this kind of principle is very useful when we want to show something globally. So all we need to do is to show the property locally. So for instance, if we can show that Tj are all larger than or equal to 0 for all j, then T is non-negative. And also, if Tj, we can show that Tj, each of the distributions are Cm, are Cm functions for all j, then T will be also Cm. So this is quite handy because we can just reduce the study of a property to a complex set, say. So so this will help us a lot in many of the applications, and we're going to see one or two later on. So let's do this, prove this gluing principle. Proof of proposition 7.2. Okay, so the first thing we want to do is the existence. So here we have two things to show: the existence of a T, of such a T, and uniqueness of such a T. So let's do first the existence. So we consider for any compact set included in omega. Of course, for a compact set, we can find a finite collection of omega j's such that K is included in union of omega j for the finite family. So what I'm saying is that there exists a finite family of indices. So this depend on K. So it's a finite subset of J, such that, so this is just compactness. K is covered by omega R in this capital R. Also, we can find a family of test functions indexed by the same capital R test functions on omega R. Each of the chi R is a test function on omega R with the property that this family of functions, test functions, are taking values in between 0 and 1, and the sum of chi R in capital R is equal to 1 on K. Okay, so the existence of such a family of test functions is so we're going to take that for granted. So if you're interested in how to construct such a family, you can search the following word. I think to some of you this might be known already. This is called a partition of unity. So we have a bunch of family of test functions. The sum is equal to 1, the identity function on a complex set, and the complex set is covered by a bunch of open sets. Then we can find such a family. So this is called a partition of unity. So this is very useful for the following reason. So now we can define our distribution T, right? So we're going to show existence. So for any phi test function whose supporting is in K, right? So K is chosen at the very beginning. So we define T of phi, right? So this is the definition as the sum over R in capital R of TR of phi times chi R. All right, so this is our definition. And so there are several things we need to show. So first of all, we need to show that this definition makes sense, right? In the sense that the right-hand side in here does not depend on the choice of the family of chi R's. Of course, there are not just one family of chi R satisfying this property. Okay, there are infinitely many partitions of unities. So what we're going to show is that this quantity does not depend on our choice of partition of unity. So to this end, so this is our first thing we're going to show. So we show that the right-hand side of the definition does not depend on the partition. Of unity chosen. Does not depend on the chosen. Okay, so the chosen partition of unity. So to this end, we are going to consider another family. So chi tilde R be another partition of unity. Satisfying the same property as a chi R's. Then we can compute then we can compute so the right hand side according to the definition. Right hand side is this guy. Okay, so what we're gonna do is to insert a 1 to this to each individual term. Okay, R times sum of chi j in capital R. The reason we can do this is because the support of this function is in omega R, right? It's actually in omega R, and also the support of intersecting the support of phi, which is included in K. And this guy takes the value identically 1 on the composite K that we have chosen already. Okay, so this guy is exactly that equal to this. So now we can use linearity to have R, J both in R, TR, phi, chi R, chi, okay, this is tilde, tilde J. Okay, so so the next step, we are going to show that this guy is nothing but Rj in capital R Tj, phi chi R chi J tilde. This is because what we do is let me just highlight the difference here. We are replacing TR by TJ, so this is what we did. So we can do this because if omega j and omega r are disjoint, then we know that the support of chi r is included in omega r, and support of chi j is included in omega j. If this occurs, the product will be 0, so that we can do whatever we want. We can replace this guy by anything. In particular, we replace TR by TJ. And then both are 0. Both terms are 0. We can do that. Otherwise, they do intersect each other. And in that case, we use the fact that TR restricted to omega intersecting omega R is equal to TJ restricted to the intersection of the two open sets. So this is our hypothesis in here, right? So this is the condition we put on the family of TJs. Okay, so either way, we can show this identity so that now we are almost done, because what we can do next is to sum over R in here. We sum over R for the finite family of capital R in capital R. We do the sum, and we know that the sum of everything is equal to 1. The sum of chi r's is equal to 1, and this gives us it remains j's. So now Tj phi times chi j tilde. Okay, so that we have shown the identity that the sum over, so we use one partition of unity or use another partition of unity, we have always the same thing. So this is what we want to show, right? So this shows that this guy is well defined. Does not depend on the choice of the partition of unity. Okay, so now we are confident about the well-posedness of this definition. So now we can move on to other stuff. We can want to show that this guy indeed defines a distribution. So to this end, we're going to show two things. To show that it is a distribution, first we need to ensure that it is a linear form. And this is okay, because if we look at the definition in here, so this is clearly linear in the function phi. So it remains to show that it is continuous So in other words, we are going to show this inequality in here for TL phi. Okay, let's do the computation. So to show the continuity, we compute T phi absolute value, and it is the sum of all the, we're going to use the triangle inequality. So compute Tj applied to phi chi j. And since we know that all the Tj's are distributions on omega j, and so that we can indeed find a ck, a cj. This is due to the fact that Tj's are distributions. So Cj constant depend only on the support of phi, and supremum for all the multi-indices with norm less than or equal to some mj. Then we compute alpha's derivative of d alpha phi chi j. Uniform norm. Okay, so this is due to the fact that Tj's are distributions. And now if we let m equals to the maximum of all the mj's, j in capital R, so then we have the upper bound. So also we're going to use Leibniz in order to separate the product. In order to separate this product, all we want to do is actually to bound this guy by a certain partial derivative of the function phi, right? So we don't want this chi function, and chi is fixed. So we want to use Leibniz rule to write it as the product of the partial derivative of phi and partial derivative of chi, and then we can bound the partial derivative of chi by its uniform norm, which is bounded. So all this is to say that by incorporating the constant, incorporating the uniform norm of chi j's into the constant cj, we can obtain such a result. We can obtain such an upper bound. So eventually, it really just remains the d alpha of phi function. And this shows that the T defined previously is a distribution. So eventually, we're going to show very last thing. Remember that we still haven't showed this property. We have defined such a thing, right? And we still want to show that it satisfies this property, the restriction of T2. We show this restriction of T2 omega j is equal to Tj. To this end, we're going to consider K compact subset omega j. All right, and so then we can find a test function in omega j, right? And this test function takes 0, 1 value in between 0, 1, and also chi is equal to 1 on this K, on the compact set. Okay, so this we can do. So it's a cutoff function, or it is a specific example of the partition of unity where we only consider the family of open sets is just one set. Okay, there's only one set, one open set omega j, and we find one function which takes value 1 on the support on the compact set K. Okay, so this we can do, and so if we choose the family chi R, that we introduced previously, to be just this one function. So in other words, for omega j, we have chi j. For omega j, we have chi j, and for all the other omega k's with k different from j, we consider the function chi k equals to identically 0. So those function doesn't count. There's only one function in our family, so we can obviously we can always do this because we can choose any partition of unity we want. Okay, so if this is chosen, then we have that for any phi test function in omega j with support of phi included in k, we can establish the following. So T of phi, according to the definition, we know it is the sum over R. It is sum over R of TR of phi times chi R. But all those chi R's are 0 for all the R except J. So it remains only one term in this definition. And this one term is Tj times phi chi. Also, we note that support of phi is included in k, and function chi takes the value 1 on k, so that this product is actually itself. It's just phi. Okay, so this finished the claim. This shows that T restricted to omega j is equal to Tj. So these two guys are same when we consider test functions on omega j. Okay. So we finished the proof of existence. So it remains to show uniqueness. So we still need to show uniqueness. Here we are. So let's consider, imagine that there is another distribution, right? So there exists, suppose there's another T tilde distribution, omega, such that T tilde restricted to omega j is equal to Tj as well. Tj already we know that it is the restriction of T to omega j. So T tilde and the T coincide on all the omega j's. This is the assumption, and we're going to argue that T tilde and T are the same thing. So to this end, we consider any k compact subset of omega, and we can consider any family chi R, so R, capital R, which depends on k, any partition of unity. So we can choose any one. And then for any phi test function with support included in k, we have T minus T tilde of phi. The goal is to show that this guy is actually 0 all the time, right? So to this end, we are going to write T minus T tilde phi sum over chi R's. Okay, so this is because we have R in R. This is because we have a partition of unity which takes the sum of everything is equal to 1 on the compact set K, and the support of phi is included in K. So using linearity, we can write it as sum of R in capital R, T minus T tilde, phi chi R. So we notice that this phi chi R, this function over here, is actually has support included in omega R. So the support of this guy is included in omega R, right? Because the support of the chi R is included in omega R. If this is the case, by using our assumption that T tilde and T coincide on omega R, omega J, for any J here, really. In particular, it's true for J is equal to R, so that this guy actually gives value 0, and the sum of 0 is still 0. So we have finished the proof. All right, done. Okay, so this shows that T is equal to T tilde. Okay, without saying. Okay, So we finished the first proposition to prove this gluing principle, which is really useful in view of the applications that I just said before proving the result. So if you have a positive, if the restriction of the distribution to subsets are positive, then this distribution is also okay, no negative, then this distribution is also no negative, right? So on the bigger set. If we can show CM, then we can show for all the small open set omega j, then it is also CM on the union of all these sets. Okay, so next thing we are going to consider product by a smooth function. So in particular, I'm going to show one result, which is a generalization of what we did previously in one dimension. So we consider null space of a product by linear functions. Recall that if you have a distribution multiplied by x minus a in one dimension, multiplied by a linear function is equal to 0, then necessarily this distribution is direct mass. And here it is the same thing. So if we have this property satisfied, so for all j and this uncertain fixed point a1, a2, ad. So this is a vector. It's a d-dimensional vector whose coordinates are all complex numbers, right? So if we have this property for all the j, all the coordinates, so then we have that C necessarily is a constant times the direct mass on the point A. A is the vector. Okay. So actually the proof is almost identical, so I only sketch it and point out where we should do something more than what we did before. Okay, so proof of proposition 3.7, 7.3. So T is the distribution such that we have this property, right? So let's just be clear. T is such a distribution for any j from 1 to d for some column vector A, AD, C, D, d-dimensional vector. So for any k compact subset of omega, and we consider phi test function whose support is included in k, and we're going to compute this. So since we want to show that T is a direct mass, eventually we should have obtained a constant times phi of A, right? So that's the goal. So we're going to make the following decomposition: T times phi of A times a test function, so that this is still a test function, plus T times phi minus phi of A chi. Okay. Where the test function chi should satisfy the property chi of A is equal to 1. Okay, so so the result will follow if we can show. The result follows if we can show the following. So this is a fact. It's also called Hadamard lemma. Hadamard. It says that for a generic test function, omega, the fact that phi of A is equal to 0 is equivalent to say that there exists a psi j test function for j from 1 to d, such that so phi of a is equal to 0. So in one dimension, we know this result already. We know that this function can be factorized as x minus a times a test function. So here we have a generalized version of that. We say actually we can find functions. Phi x can be written as the sum j from 1 to d and xj minus aj chi j, psi j. All right, so we can find all these functions psi j such that, again, we can factorize the function somehow as the product of linear function times psi j, a linear combination of those. Okay, so this is good because of the following. Because we realized that by our choice of the function chi of a is equal to 1, so that this whole thing takes the value 0 at point A. If this is true, then we know that there must exist the test functions psi 1, psi d, such that this can be written as such. Okay, so this shows that. Okay, so indeed, we're going to conclude. So the t applied to phi minus phi of a according to the lemma is equal to j from 1 to d. Then so t applied to xj minus aj chi j. We have used linearity and the lemma, which is nothing but j from 1 to d xj minus aj t by using the definition of a product. And we know that such a thing is 0, so that all these guys are equal to 0, implying that the second term in my decomposition is equal to 0, so it remains only the first one. Implying that t of phi is equal to so t chi phi of a, which is constant times Dirac mass at a applied to phi, and this constant c is nothing but the value here, t of chi, which is a complex number. And so we're finished. Okay, so this fact can be we have already shown this fact in dimension 1, and a higher dimension can be shown by using induction. So we skip the proof of that fact. Okay. So now let's move on to partial derivatives of distribution. So in other words, we're going to consider so this time null space of derivatives. So again, this is the generalization of the result that we have already seen in one dimension. So there we have that if a distribution has 0 derivative, then it is necessarily associated with a constant function. Okay, so that's the conclusion. So here we have the same kind of result, but we need to guarantee that this function, this distribution T has 0 derivative for all its has a partial derivative for all its components, 0. And if this is the case for all j, right, partial derivative with respect to the jth variable of t is equal to 0 for all j, then t is constant. So this let's show this result again. I'm going to sketch it without giving all the details. So proof of proposition 7.4. So this time we're going to consider T a distribution such that the partial derivative with respect to ith variable is equal to 0 for all I. And then we consider any compact subset of omega and any 0, so any phi test function with support in K. And then we calculate T of phi. So the goal is to show that T is a constant, right? So, so in other words, the ultimate goal is to show that this quantity is equal to a constant times the integral of phi, right? So to this end, we're going to make a decomposition. So T times the integral of phi times test function plus T times phi minus the integral of phi, the test function, where we're going to choose this chi to be a test function in omega, such that the integral of phi chi is equal to 1. Okay, so the result will follow by characterization of the functions with zero integral, actually. So this guy will have zero integral because of our choice of chi. If we can write it in another way, write it as a derivative of something, then we can make use of our assumptions. So this is the key idea. So we are going to show a characterization. So the result follows by a characterization. Characterization of the test functions having vanishing integrals. Okay, so this is another fact, which is reminiscent of what we did before in one dimension. So again, we consider a generic test function, T of omega. Then we know that the integral of phi is equal to 0, so the vanishing integral is equivalent to say that there exists a function, there exists a bunch of psi 1, psi d, family of test functions, such that the function phi can be written as the sum of partial derivative of those functions psi j. Oops. Okay. All right. So this fact we know how to show actually in one dimension, and again we can use induction to show this in higher dimensions. So I can skip the proof of the fact. Let's just move on. And I claim that the result follows if we have this characterization, and indeed, in such case, so if we consider T of, so the second term in my decomposition, and this guy can be written as T times the sum of J over J from 1 to the partial derivative dj psi j. And this is nothing but a negative partial j, so I take the sum, j from 1 to d by linearity, and then we pass the derivative to the distribution t with a negative sign, so we have this. And here we can make use of our assumption that dit is equal to 0 for all I, okay? So now we see why we need this result for all the I, because if only one of them is 0, it does not guarantee that this guy is equal to 0, right? So we need all of them to be 0, so that this whole thing is equal to 0. And since this is equal to 0, the second term disappears. We have T of phi equal to T times, no, T of chi, which is the constant, times phi, which is constant applied to phi, where the constant C is equal to this quantity. And this shows that T is a constant, which finishes proof. All right. Very good. So we are done with another topic. So next thing we consider convergence. Okay. So convergence is obviously very important in distribution, in particular for this for the reason of the this regularization result I'm going to show. So let's look at what it says. It actually says that for any distribution we can use a C infinity function to approximate it. So this is basically what it says. And more precisely, we consider a distribution T, and this is a test function with support inside the open ball with radius 1. So my B1 denotes an open ball with radius 1 centered at 0. Okay, so we have such a test function supported in B1 with integral 1. And then we make a scaling of it, rho epsilon. And this scaling is chosen in such a way that the integral of rho epsilon is always 1, no matter how small epsilon is. So this is invariant. If we take the integral, the scaling doesn't change anything. Okay, so the claim is that this function rho epsilon is smooth with support in there. So this step is actually a trivial step, since rho of x is 0, is non-zero only if x is inside the ball with radius 1. And if we look at this function, it says that the support, so this guy will be non-zero only if y is within a distance epsilon to the point x, okay, which is the same thing as a support inside the ball centered at x with radius epsilon. And it's smooth because rho is a smooth function. Okay, so it's also, this guy is also a parametrized family of test functions. Right? So these are all test functions indexed by x. So now what we claim, which is more interesting, is the following claim. We say that f epsilon defined as t applied to the test function. This is well defined because t, this is rho epsilon, as I just said, it's a test function. It's well-defined object, and also this guy has very good regularity. It is actually a C infinity function. It defines a smooth function on the set, on the subset of omega, which is so here. Look at the definition on omega epsilon, which is slightly smaller than omega. So let me draw a small picture of it. So say this is omega. Oops. Say this is our omega. Okay, it could be an infinite set. It's open set omega, and the omega epsilon is actually a subset of omega with the property that all its sets are within distance, or has all the points inside omega epsilon has a distance larger than epsilon to the boundary of omega. So this is called omega epsilon, and this guy over the bigger set is actually called omega. Right. So this is what we have, and here the distance is epsilon. Distance is epsilon. Okay, so the function is well defined on that because okay, so for all the x inside this omega of epsilon, if x is chosen inside here, then the ball centered at x with radius epsilon will be included in omega. So this is epsilon will be included in omega, and so that this guy is well defined. Okay, t of rho epsilon x will be well defined, and since the function the t is just the object defined on omega, right? So we cannot consider points which are outside of omega. Some points in here doesn't we don't allow that situation. So f epsilon is well defined on omega epsilon. just for this reason. And what is more interesting is actually this is a C infinity function. It is a smooth function. And also, this smooth function we applied to a generic test function. We know that this converges to our distribution applied to the generic test function phi. Okay, so this gives us a convergence result actually. We have a C infinity function which converges to T. So we're going to show something even stronger, which is to say that we can find C infinity with compact support. We can find test functions to approximate T. So for now, we just have a C infinity function to approximate T. Okay, so just one more remark. So notice that this guy in here is well defined because when epsilon is very small and rho, since this phi function has compact support in omega, when epsilon is a very small omega epsilon, this set omega epsilon will include, so this will be the function k, this will be the support. So this called, okay, let me just forget about k. So this will be the support of phi, which is a compact set. Okay, so when epsilon is sufficiently small, the compact set support of phi will be included in omega epsilon, so that this everything is well defined because this integral is nothing but integral on the support of phi. Okay, and the support of phi is included in omega epsilon. So this guy is well defined. Okay, so in order to show this result, actually we need two different lemmas, two propositions. So it is more or less straightforward if we understand the propositions. These two results are fundamental and very useful also, not only for proving this regularization result, it can be used everywhere, and we'll see later on. So the first result is an analog of this derivation under the integral sign in Lebesgue's integration theory. Right? So if you have you have a family of functions, Lebesgue integrable, and you want to derive with respect to a parameter, then you can do that under certain conditions, right? So this is the distributional version of that fact. So now we derive a bracket in a family of bracket. Okay, so this is nothing but if we derive the function inside the bracket. So we are sort of interchanging the order of a bracket and a derivation. So this is the first result. And the second result says that we can do integration under bracket, and this is like the analog of Fubini theorem in integration theory again. So where we can interchange the order of integration. So this is exactly what we do. We interchange the order of a bracket and an integral. And we know that bracket, when we have a t is a L1 log function, this is nothing but the integral. Okay, so we are interchanging the integral. So justifying my claim that it is an analog of the Fubini theorem. So both are very important in integration theory, and both are important. These two facts will be important in distribution theory. Okay, so let's show proposition automatically, right? Let's show proposition 7.4, 7.5 directly by using these two propositions, okay? The proof is straightforward once we know these two things. And later, after the proof of proposition 7.5, I'm going to show the proof. I'm going to give the proof of these two facts. Okay, proof of proposition 7.5. Okay, let's look at again the definition of a epsilon. So there are several things we need to show. We need to show that epsilon defined as such is a smooth function. I already explained why it is well defined down here. So it remains to show is that this guy is a smooth function. And for this, we are going to use proposition 7.6. Okay, so it says that if you have a distribution T and a function which is a C infinity on the product space, omega times RP, Euclidean space, so p-dimensional Euclidean space, such that the projection of the function phi to the first coordinate is a compact set. Okay, so this is a so in particular, if we have a test function on the product space, then this property is satisfied. Okay, and we are actually in that situation in the proposition 7.5. But this is a more general fact. We can consider C infinity function whose support when projected to the first coordinate is a compact set. So if this is the case, T phi given as such, then the map defined as T applied to phi of Z. Okay, so T is X on this variable dot, and Z we leave it as a parameter, so this defines a function of Z, right? So this map we're going to call the G of Z. And the claim is the G of Z is C infinity. It's a smooth function. And this is exactly what we wanted because F epsilon is defined exactly as this. Okay? And the property is satisfied because we are in a very good situation where the projection of the thing to the first so this function yesterday C infinity with compact support on the product space. So we are by using this we know that F epsilon is a C infinity. Also we can take derivative for this C infinity function, and this is nothing but take the derivative with respect to its variable, Z variable. Okay, so this is the first claim. Let me continue with the proof. F C infinity really follows from proposition, the first claim of proposition 7.6. And we still need to show another claim, which is the convergence of F epsilon, the F epsilon applied to phi converges to T applied to phi. Okay. For this matter, we are going to compute F is omega and epsilon of X applied to test function phi. Okay. And so let me just write one more step, then you will see what to do next. So recall that this F epsilon is actually defined as the bracket T applied to rho epsilon X minus dot D. So phi. So this is the sorry. So this guy is nothing but F epsilon of X. So now we integrate phi x dx. So now it is pretty clear that what we're going to do next, right? So we have integral of a bracket. So we want to interchange the order of bracket and integral by using the proposition 7.7 in here. So we're exactly in this situation, and all this the definitions are satisfied, so that we can apply it. And using this result, using proposition 7.7, so we have that is equal to T applied to omega rho epsilon X minus dot phi x dx. Okay, and eventually this guy converges to T of phi because T is a distribution, so it has continuity, and also this family of function indexed by because this function rho epsilon X minus y 5x dx. This function converges to phi in the space of test functions, right? So this is because rho epsilon is a approximation of identity, actually. So we can check easily. It's a C infinity function with compact support with all the good properties. We can check very simple. It's a straightforward exercise to show that this guy actually converges to phi in the space of test functions, meaning that we have uniform convergence for this function for the difference of the two functions to 1, and all its partial derivatives also converge uniformly to 0. The difference converges to 0 uniformly, and all its partial derivatives converges to 0 uniformly. So so this is true, then we are done. So we finished the proof. Okay, so it's really a combination of the two propositions 7.6, 7.7. So next, I'm going to give the proof of these two facts. Let me start with 7.6. Proof of proposition 7.6. Okay. All right. So there are several things we need to show. We need to show that this function g is C infinity. Also, it satisfies this property. This d alpha g is equal to t times d alpha to the function phi with respect to the z variable. Okay, so first thing first, we need to show g is differentiable. So this is the first thing we want to do, and then we gonna once we show that g is differentiable, we can iterate the argument to show g is C2, C3, etc. So the difficult part is show that this guy is only the first step, actually, to show that this guy is C1. How to show that? Let's consider. Okay, let's consider this the compact set. Let me make the compact set explicit. So K be the compact set. Such that the projection to the first variable, x variable of the support of phi is included in K. Okay. So this is by assumption. We take phi as this form, and we consider z naught, fixed z naught, and so we're going to show that this function is C1 on the point z naught for all the z naught. Right? So for z naught fixed, h small vector in Rp. So by using Taylor's formula, for C1 for C infinity functions, actually phi is assumed to be C infinity. So we can have Taylor. So here we only need to do first order expansion. So z naught plus h minus phi of x z naught. Okay, two variables. So the increment is equal to Taylor's formula. I from 1 to d, we can take the partial derivative with respect to zi of the function I. X doesn't change, then z naught times h I, the s coordinate of the vector h. So this is the first term. Then there will be a reminder term that we're going to call r of x z naught h. So now we actually have a explicit form for this remainder r. It is given by integral form, so twice. So alpha is equal to this time 2. also h to the alpha factorial, where we know that h is a vector. So what does it mean? H to the alpha. H alpha it means that h1 alpha 1 hd alpha d. Okay, so recall of the notation. And alpha factorial is equal to alpha 1 factorial alpha d factorial. Not alpha p factorial, because p-dimensional vector. Yes, this notation. So this is a constant eventually. And constant times this integral 0, 1 and 1 minus t. Alpha's derivative with respect to the z variable of the function phi. X doesn't change, and z naught plus t times h. Then we integrate dt. Okay, so this is our Taylor's formula. So in order to show that it is, so the function, we're going to show function g is C1, right? So we're going to express this this g function as a linear part plus a small part, which a linear part, and a small part, which goes to which is of the order a big O of h squared. So that's our final goal, and to that end, we're going to make use of the explicit form of this remainder. We're going to have some bond. So in order to bond this, in order to bond this guy, we have so T of R. So this is the goal. We're going to compute the T of R and try to argue that this T of R is bounded by h squared times a constant. Okay, and to this end, we need to know that this guy is indeed a test function. Notice that this function x maps to x r of x z naught h is a test function. So this test function on the x variable, test function with support in k, right? With support in, okay, it's not phi itself, it's actually just the first coordinate. So with support included in k. So due to our assumption on phi. So for some universal c and m, which might depend on k but nothing else, we have t applied to this z naught h. So t applied to this, we're going to have a bond. And we know that it is because of the fact that it's a test function with supporting k. We have c times the supreme of beta, multi-index beta with norm less than or equal to m. And then we have beta r of so x variable. Let's do the x variable. Then zeta naught and h are fixed. Then we take the uniform norm with respect to the dot variable. Okay, so this is we have used the fact that t is a distribution. Hence, for h with a norm smaller than 1, so vector with norm smaller than 1, this the partial derivative beta with respect to x variable here is actually x variable, right? Because here the variable is in x. The x variable of this r, then let's just write x h. We want to bound this guy. We call it ultimate goal is to obtain the h squared, and this guy is equal to, so we have an explicit form for this guy by using Taylor expansion, but this is the remainder in Taylor expansion, so it has an explicit form, and this is nothing but the twice twice the sum when alpha has norm 2. Then we do this h alpha and the alpha factorial thing, and integral 0, 1, 1 minus t of all the partial derivative, right? So we take the partial derivative with respect to its the form of r. So partial derivative with respect to x. So d beta with respect to x of this guy. We can interchange the order of integration and the derivative because by using because all the functions are test functions, right? So we can do that. Dominant convergence theorem justifies. Okay, so the point is that now we have an explicit form for. So now we have actually this here is alpha respect to z, and we okay I don't remember what it is. Phi of right, phi of x z naught h apparently so z naught plus th dt. So this is what we have, and we want to have an upper bound. So first we realize this guy is actually bounded by the norm of h square because alpha, the norm of alpha is equal to 2, right? So this is a simple bound, and we have twice that h squared norm, and alpha we can just forget about it. It's so 1 over alpha factorial is bounded by 1, and then we look at this quantity. T is taken from 0 to 1, so that here this point is inside the ball center at 0 z naught with radius 1 because h has norm smaller than 1, t in between 0 and 1. So all that to say that this guy is bounded by the supremum when x is in K and the z is in B. It's a ball centered at z naught with radius 1. So then we take the partial derivative with respect to x, with respect to z of the function phi xz. Then we take this is the uniform. This is the supremum of this function on this compact set actually. So this is a k times b1 of z naught is a compact set in the product space. And this is a C-infinity function, so everything is bounded. So this guy is bounded, and we indeed have a big O of h squared, and the constant depend only on the value z naught and nothing else, right? So depend on function f phi, of course, and so locally we have around z naught, this function, this remainder is of the order h squared. Okay, hence we can express g of z naught plus h minus g of z naught. So this is the g function is just t applied to phi of not z, right? And this guy, if we compute the difference, we can we need to so let me just write it out. So this is actually t applied to phi of not z plus h minus phi of not dot and then z naught. Okay, and we have used the Taylor expansion for this quantity, and we have expressed it as a linear form times plus a remainder term which is of the order h squared. So this is done previously in this formula, so just replace the difference by this new formula here, and the estimate for t of r dot. Then we have the following. Sum over, so this is the linear part, I from 1 to d, and t applied to dot partial zi, okay, the z variable, the Taylor expansion part, and this is phi not dot z naught times hi. So this is a linear part. Then we have another part which is t applied to the remainder r, and that one is bounded by h square. So h square. Change it. All right. So so this shows that the G is actually differentiable with partial derivative is equal to. So now so hi is just constant. Let me just rewrite it. Hi, just write it outside of the bracket. And if G around point z naught has the following expansion, then the partial derivative as partial derivative of G will be given by this quantity in here, right? So this the gradient will be the vector given by this kind of thing in each of its component. So the partial derivatives is given by this. This is Z naught. Oops. Okay. All right. So this we have shown that G is differentiable, right? And we so if we apply Taylor expansion, again, Taylor's formula, first order Taylor's formula to the partial derivative to this guy in here. So to this guy, we use the same trick. And then we can argue. We argue that this guy actually can be is also differentiable. So the partial derivative I, partial derivative, okay, the partial I of G is also differentiable. In particular, it is continuous. Applying Taylor to the test to this partial zi of phi test function proves that partial ig is differentiable. So continuous. And this shows that G is in C1. Okay. So applying the trick, the whole trick of doing Taylor expansion, and then and show this the expansion term of with additional remainder. We can show that if we apply this whole trick to the gradient of G, we obtain G is in C2. We can iterate and see that G is actually C infinity. So this finished the claim that. Okay, this finished the proposition actually, because we have already done the partial derivative thing. So this formula is given, and this is exactly what we wanted to show in here in this proposition. Right? So partial derivative, we can pass it inside the bracket to the test function. Okay, this is what we show, at least in the case alpha, the multi-index alpha has norm 1. And so by induction, of course, we can show this for all the alpha, for all the multi-indices. And this finished the proof. Okay, very good. Next thing we want to show is the integration and the bracket formula. Proof of proposition. 7.7. So it's analog of the Fubini theorem, we call that. So it's forbidding is very important, right? So this is also very important in theory of distributions. So here we're going to show this this result for only p is equal to 1. So here p is the dimension of this another. So we have a product space omega times Euclidean space, dimension p. So we do this for p is equal to 1, and we can use induction to prove a general result. So only prove the case p equal to 1 and left the general case to you. If you are interested, it's just by induction. Okay. So we're going to all right. So in one dimension, so what we can say about this function is that we can find a capital A. So yeah, since this phi function is a test function on the product space. Now p is equal to 1, so we have is r, just r, and there exists an A positive number such that the projection of to the y variable, so the second variable of the support of a phi is included in negative A and A. Okay, just by the fact that phi has compact support. So now we set g of z. So we define new function definition. So t applied to the integral when t less than z, phi t dt. So this defines a function of z. So z is in here. It's a family of functions. So we apply t to this function, to this dot variable in here, and the function is indexed by z. Okay, so the observation is that this function of g is actually C infinity by using our previous proposition 7.6. So we know that this guy is actually C infinity. So g is C infinity, and we can compute its partial derivative. So it's just derivative because we're in one dimension. And the derivative of this function g on the point z is given by t times derivative of this whole function, which is given by phi in here. So phi dot z. So if we compute a t applied to phi dot z dz, we just need to look at actually g of A. Okay, so because A is sufficiently large, so negative AA contain the projection of the support of phi to the y variable. So A is sufficiently large such that the integral, when the integral stop at A, or we compute the whole integral, we obtain the same thing. Okay, so in other words, we have this. We can just integrate its derivative, and for the same reason, so we don't need to consider t less than a. We can just consider integral on the whole real line because a is sufficiently large outside of the support of the function. So by using the definition, by using this computation that we did already, so we have the formula, and we just compute the integral of that thing, and this is precisely what we want to show. Okay, so this proposition is actually pretty simple. Once we know how to do a differentiation under bracket, we can construct our function and then do the differentiation, and the result follows straightforwardly.
Okay, so as I mentioned already, any distribution can be approximated by a sequence of test functions. So in proposition 7.5, we have shown that we can construct a C infinity function which converges to T. But this C infinity function may not be having a capacitor port. So indeed, if we consider T, which is a distribution, okay, so T is a distribution, something like it's not C infinity, it's a continuous function which is never vanishing, it doesn't vanish at all on the whole real line R. So in that case, there's no hope that this function has capacitor port, because this is just if T is a continuous function, this is the convolution of the T with respect to rho epsilon, which examine the local behavior of the continuous function around a point x, regularize it so that you have C infinity curve. But for any function, any point x, if this continuous function does not vanish at all on the whole real line, then this function doesn't vanish either. Okay, so this function doesn't work. This function is C infinity, but it doesn't have a capacitor port. So what we need to do in this corollary is just to do a little adjustment to this construction in here. So what we do is to multiply this function by a test function on a sufficiently large set. And if along the sequence our test function support is growing, it's growing larger and larger until it reaches the open set omega, then we are done. So this is the basic idea. Let's do the proof. Okay, let's another page. So proof of corollary 7.8. Okay, so the idea is to construct test functions, right? So construct test functions on the growing domain, and this growing domain we're going to define it as omega j, and omega j will be subset of omega such that the distance between x and the boundary of omega is larger than 1 over j. Okay, it doesn't reach the boundary, but as j grows to infinity, it will grow to the whole omega. And also, we want this set to be a bounded set, so that we can have. So this is for constructing a test function with capacitor port, right? Okay, then easy observation is that this omega can be obtained as the union of those omega j's. So this is the first observation, and also we see that this omega j, the closure of omega j is included in omega j plus 1. Okay, so now we let chi j, so this is our test function. We're going to multiply this test function by the function f epsilon we already considered. Now this function this chi j is a test function in omega, which takes value. So this guy is a cutoff function. It's going to take the value 1 on omega j bar. Okay, and it's a test function. It's a test function with capacitor port. So we want to have this. This is a compact set because of the second restriction for the sets, right? For the set omega j, x is bounded by j, so that this is a compact set indeed. Okay, so now we can what we can do is to choose epsilon j, which will be smaller than 1 over j, okay, such that the support of chi j is okay. So now spot of chi j is included. So this we can do because this guy has compact support. As long as epsilon j is super small, this is guaranteed. So recall that my notation for omega epsilon is the subset of omega such that the distance between x and omega, the boundary of omega, is larger than epsilon j. Okay. So when we take epsilon j is super small, then this guy will cover a compact set included in omega. Okay, so this we can do. So now we can define our new sequence, so which is just a slight modification of what we have before, the F sequence, which takes there are two situations. If x is inside omega j, omega epsilon j, so if it's inside that thing, then I'm going to just use the product between chi j, the cutoff function, and f epsilon j of x. Okay. So that this function actually is, so this function is still C infinity because it's the product to C infinity function. And it's gonna take the value 0 if x is in omega subtract omega epsilon j. So in this slide, this like is in the small annulus, right? It's just this very thin band around the boundary of omega, and that thing is equal to 0. So this is this is okay because we can because the chi function takes the value 1 on omega j, and on omega j, and okay. So I also want this function to be actually containing okay, let's just forget about this two difference. Just to take the product. So now the function in here, the function is already well defined. It's a well defined object. It is let's say okay. See the support of chi j is in omega. I need to take omega j in here, right? Support of chi j is in omega j, j plus 1. Yeah, so this is what I want to do. The support of chi j is in omega j plus 1, which is strictly larger than omega j bar. Okay, and it is equal to 1 omega j bar. Such a function exists. There's no problem. And so now it is well defined. Everything is good. So that the support is included in there, and the function is well defined on omega epsilon j, and the support of chi j is included in there. Is included in there so that for the product will be 0 for any point outside of the support of chi j. Okay. And in particular, for x outside of so here, indeed, I still need to give a value. So x in omega epsilon j, x is not in omega epsilon j. The function is defined on omega, subtract. So we only need to consider the complement of omega epsilon j in omega. So so this function will already take the value. It's still a smooth function, and inside this interval it is already on a compact subset of this. we have already so the product will be 0 outside of a compact subset of this quantity, so that by extending this function, we extend the function by 0 to a larger set. There's nothing, there's no problem. Okay, so we still have a C infinity function, and support of this function will be included inside a compact subset of this omega epsilon j. So I need to make this distinction because f of x for x outside of omega epsilon j is not well defined. This function is only defined on omega epsilon j. Okay, so now by doing this maneuver about the support of chi j's, I define still a C infinity function on the whole omega, and it has compact support. And the point, finally, the point I'm trying to make is that for any phi test function with compact support, so with support of phi in certain k, for any k, right? So the integral of for any k compact subset of omega, consider all the test functions. So we do the integral of this. Okay, so we're in business, dx. So now this is nothing but the integral on omega epsilon j, right? Because outside of it is just 0. So, and on this subset is this thing equals to chi j of x f epsilon j of x dx, phi of x dx. Okay. And now, so what do we? I want to show is that this guy is equal to omega epsilon j, f epsilon j. Let's just forget for 1 second the chi j, forget about the chi j. Then this guy will converge to T of phi. That's what we wanted. But there's another term which is 1 minus chi j x still on this subset, and f of psi j x phi of x dx. So the claim is that this guy in here, let me just highlight this formula in here. The integrand we have for the second integral is equal to 0. So the integrand is equal to 0 as j is super large. If j is very large, then 1 minus chi j, so this is observation, is equal to 0 on omega j bar. Okay, this is by the definition of chi j. So and omega j bar contain support of phi, contain k, which is larger than the support of phi, when j is very large. Okay, so that the product eventually actually becomes here. The point is that this guy has support in k, and this guy has support. The support of this guy and support of this guy has are disjoint, so that the product always equal to 0 when j is super large. So the conclusion is that the second integral doesn't matter, and the first one converge to. So what do we want to show? Okay, so this finished the. So by proposition 7.7, this finished the proof. Okay, so the last result that I'm going to do in this section is a quite interesting result, which will be useful in PDE. So now we consider a partial derivative of a distribution, and we assume that the partial derivative is a continuous function. Okay, consider a PDE, and then if you assume that so the partial derivative of t is equal to a continuous function, right? So then we can actually prove that t must be C1. So this is a useful fact. So proof of corollary 7.9. So this is largely the result of today's lecture. So first reduction is that we can make use of the gluing principle in order to show this this result hold. So t is C1 on the whole omega. We can just show that t is a C1 on a bounded open set. Say so any bounded open set. So let's consider for instance we can consider the unit cube. So by gluing principle that we have shown already, gluing principle, which is proposition 7.2. We can just show, we suppose without loss of generality that omega is just S, the unit cube. Okay, open unit cube. And we're going to write fi for the derivative of t. Okay, we assume that it's a continuous function, and we're going to use fi to denote this continuous function. C continuous on the cube. And now we consider k, which is a compact subset of the unit cube, such that so k is included in, okay, so this is always true, included in S epsilon naught for some small epsilon naught. I recall that this guy again is given by the points in the open cube, unit cube, such that the distance between x and the boundary of S is larger than epsilon naught, right? This is the definition of this this set, smaller set, a shrink cube by a small epsilon. And if epsilon naught is a small, then the k will be included in this shrinked cube. Okay. So in order to show this result, our strategy is to use approximation. We're going to show that this t can be approximated is actually the uniform limit. Is the uniform limit of a sequence of continuous function, so that the limit will also be continuous, right? So, and also its derivatives is a uniformly convergent sequence, so that eventually we show f the t as a limit is a C1 function. So the idea is to use the approximation, and we're going to make use of the proposition, this regularization result. Okay, so the regularization is the following. So we define as before, epsilon of x to be t our distribution in this corollary, and we're going to compute t applied to rho epsilon taken as before. We already know that this is a C-infinity function on S epsilon. Okay, so this is the content of proposition 7.5. So now for any epsilon less than epsilon naught, if we take the partial derivative of f epsilon, so what do we have? We can make use of the proposition 7.6, which says that we can actually take derivative under the bracket sign, under the bracket symbol. So we're in this situation. So take the derivative with respect to this variable, and we're going to have t x variable, right? So rho of epsilon x minus naught dot. And it is the same thing if we compute yi's partial derivative, right? For the whole thing with a negative sign, because there's a negative sign here. So now we can make use of the definition of a derivative for distribution. So we can pass the derivative back to the distribution. We have a dit applied to rho epsilon x minus dot. We have this identity. And recall that we have denote the dit by the function fi, which is continuous function. So now it is the integral of fi of x, rho epsilon, so they call it y, rho epsilon x minus y dy. So this is what we have. We notice that this is actually a convolution of a continuous function with a approximation of the identity. So this converges uniformly to fi. Uniformly, and on any compact subset. So in particular, it is true for the compact subset that was chosen in the beginning, subset of S. So this is good. We have a convergence of the partial derivative. So this guy will be also continuous. And also we show that for any, we're going to show that f epsilon also converges uniformly. If we show both, then we have a limit which is C1. So in order to do this, we are going to introduce auxiliary test function we call chi. Chi is a test function in S with integral 1. So then f epsilon of x minus integral of f epsilon of y times chi of y dy. Okay, so so first thing I want to point out is this guy will go to this is just a complex number because the integral of a function which converges to according to our proposition 7.5. This guy converges to t of chi. Okay, the regularization result. So this sequence of complex number converges. So in order to show that this guy converges uniformly, we only need to show that the difference converges uniformly, and that we can do by using Taylor expansion. So now, first thing we want to write it as we introduce artificially integral for the f epsilon x times the integral, which is 1, right? The integral of chi. So we put things together. We have f epsilon of x minus f epsilon of y rho of it's a chi of y dy. So this is what we have, and we use Taylor expansion for the difference of the f epsilon function, and we obtain I is equal to from 1 to d, okay, and 0 1 integral. So we have xi minus yi, the difference, and di with respect to the, okay, there's only one variable, it's just the di, f epsilon times of x plus, no, y plus t times x minus y. Then chi of y dy dt. Okay, so since we have already shown that this guy converges uniformly, and here we have another thing in here, and this guy will converge uniformly. The f epsilon function will converge uniformly because this function, the partial derivative the di f epsilon will converge uniformly, and the expression in here. So this shows that the family f epsilon as epsilon goes to 0, just f epsilon, actually converge to a certain f. This is just uniform convergence, uniformly on K as epsilon goes to 0. Okay, so the partial derivative converges uniformly to a continuous function, and the function itself converges uniformly to, so this time also a continuous function, and this shows that f as a limit is actually C1. And this f is the limit of f is the limit of this quantity, right? F is the limit of this quantity, and we already know that the limit of this quantity must be T of phi. And this actually shows that f is T restricted to the compact set. Okay, and just recap what I just said. So f, first of all, is in C1. The limit is C1, and by using the proposition 7.5 again, we see that f is T restricted to S. No, K is compact subset of S. And since K is arbitrary, compact subset of the open unit cube, we have T in C1 on S. And this finished the proof of the corollary. Okay, so this is it for today's lecture. Today we have considered several generic and useful properties of distributions with several variables, and among which the gluing principle is quite useful to do a localization argument. And the regularization is very important because it allows to do approximation of any distribution by a test function. Also, there's two computational tricks which will be constantly used in the following. These two tricks are both very important. Okay, it's good to look at it, to check a few examples if you to see whether or not you master these two techniques. And so next time I'm going to cover another topic called the jump formula. Okay, so see you in another video.